Okay, this is 2.2 from the textbook. We're looking at enthalpy change. So this little symbol means change for enthalpy. Exothermic reactions is what we're mainly looking at. Energy profile diagrams, including activation energy, thermochemical equations, calculations to find the enthalpy. And this is not in the textbook, but we'll look at some exam style questions. Okay, so energy profile diagrams, if that's what you're asked to draw, this is what the beginning of what they are. They're basically, this scale here could be like empty, have nothing in it, or it might have the kilojoules difference. So there's some random line where the amount of energy in the reactants is drawn, and then another line where the energy of the products is drawn. In this case, you've got more energy in your reactants than the products, so you've released that energy as heat. So this is an exothermic example. In this case, you've got a certain amount of energy in your reactants, and you've added energy to give the energy that's in your products. So the change in H is positive for that one. The energy released or absorbed during a chemical reaction is called the heat of reaction. Sometimes the heat of combustion you might see. So it's the amount of heat that's been released or taken in. It's equal to the difference in the enthalpy or energy between the reactants and the products. So like I said, that little symbol, I think it's delta, means change in energy or change in enthalpy. So the actual number that you're quoting here has come from this. That's the energy in your products, what you ended up with, minus what you started with, the energy in your reactants. So if the energy is endothermic, and you started with a certain amount of energy in your reactants, and then you increase to that to get to a certain amount of energy in your products, then your reactant number, the enthalpy, is a lower number than your product number. So if you're taking away less than what you've got, you're going to end up with some positive number. But if your reaction is exothermic, so you start with some amount in your reactants and then you go down to some amount in your products, then the reactant number is actually larger than the product number. So if you're taking a larger number away, then you're going to end up with a negative number. So reactions which lose energy are exothermic, and they're the main ones that we're going to be looking at. They have a negative enthalpy. So thermochemical equations are basically the same as any equation. The only difference is that you're showing the change in H. So these show the energy released or absorbed during the chemical reaction, and the energy that is released or absorbed is measured in joules or kilojoules generally. Is energy absorbed or released in this equation? Is it endo or exo? So we're looking at this equation. Has it released 2,803 kilojoules? If it released it, if it exited the energy, then it would be an exothermic. If it took the energy in, then it would be going in endo, it would be an endothermic reaction. So is this an endo or exothermic reaction? So do you remember from the previous slide we looked at if it's positive, it's gone from the reactants are here and then they've increased to the products, so it's positive. Your product number is larger and you're taking away the reactants, so it's positive. Do you recognize what equation this is? Carbon dioxide and water being stuck together to make glucose and oxygen. Do you know what it's called, this reaction? It's photosynthesis, when plants take in carbon dioxide and water and make glucose and oxygen. So they take in light energy, so it's and then they convert that into the chemical energy in the glucose. So when you look at these, even though the units on here, which you need to include, you don't have to write the plus, but if it's minus, you'd have to write the minus. and it's kilojoules per mole. So even though it says kilojoules per 1 mole, it doesn't actually mean per 1 mole. It means this is the amount of energy for however this equation is written. So in this case, you've got 6 carbon dioxide molecules and 6 water molecules. If you had 6 moles of this, 6 moles of that, you would take in that amount of energy. Okay, so just ignore that per mole. This is, in this case, this is for 6 moles. All right, so the change in H, if we swap the equation around, so the reaction where you start with glucose and oxygen is what humans and everything, animals do, respiration. So we're going, the reason that we're all hot is that we're releasing this energy as heat. We're undergoing exothermic reaction inside of us. So we've started with, if we release it, release the energy, then we start with a certain amount of energy and we drop down to where the products are. So the energy of the products minus the energy of the reactants, you're taking away a larger number, it's negative. So you must include this negative. You can see here I've made a bit of a mistake, haven't I? What have I dropped off there? This would be kilojoules per mole, like that one. So if you reverse the reaction, you just change the sign. If the reaction is doubled or halved, if you're given a reaction and then you're given another reaction and it's doubled, so if this had 2 of those and 12 and 12 and 12, then you would just double that. If it was half of this and 3 and 3 and 3, then you would just halve that. So if the reaction is doubled, the energy is doubled. If it's halved, it's halved. At the moment, that seems obvious and sensible. That we're going to look at something else like this, changing reaction, but it's what we do is not as straightforward. So don't get, this is nice and straightforward. Don't get this confused with a later thing that we do. Obviously, we can just do these things in our head, doubling and halving. But if it's an unusual number, so, you know, if this reaction, if we had 3/4 or whatever of that, then you just use your ratio. So you're relating how much, this is a 1 to 2,803, and then however many moles of glucose you wanted to know, you just do a ratio to find out the amount of energy. Okay, so this is the practice for that. So you notice the reaction is 3 moles of iron for every 2 moles of oxygen, giving you an iron oxide molecule. So for that, you release, it's exothermic, negative, exothermic. You release that amount of heat. So when you look at this reaction is the same, but reversed. So in this case, it's exothermic. What do you do when you reverse it? And it's also twice the amount. So what do you do when it's doubled? So the reaction has been reversed, so the sign changes. So the change in H is going to be positive. So you work out how many moles in the equation. So you've gone from 1 to 2, you've doubled it. Identify the magnitude, so you're just going to double that. So it'll be 1,121 times 2. So that's the answer. All right. Okay, these are energy profile diagrams, just like we had before. You have a certain amount of energy in your reactants, and then you draw another line for the products. It's gone from this amount of energy down to that amount of energy, therefore you've released energy. So this is the exothermic. You've dropped in energy. So we've added this extra sort of connection between them. So a classic reactant that's going to lose energy and become a product with less energy a combustion reaction. So if our reactants, say if you had a piece of paper and then you burn the piece of paper and you end up with just a pile of black ash, obviously that black ash has a lot less energy than the paper. So the thing is, though, that the molecules in the paper are not going to react with the oxygen in the air. They just sit there, don't they? So you need to break the bonds. So you have to, one atom is bonded, electrons moving backwards and forwards with another atom. You need to break that bond to start with before the carbon in the paper can react with the oxygen in the air and make carbon dioxide. So you have to break the bond. So you have to, that's why we light a match to hold it to the paper. You need to give a little bit of energy to break the bonds to start with. So you add some energy to break the bonds to start with, and then once the carbon and the oxygen are starting to get together to make carbon dioxide, energy will be released. So energy is released here. So the difference between what you've added and all of that energy that's released, this difference, is the enthalpy change. This is the actual energy that's been released overall. So if this reaction is what happens when we take in respiration, we take in sugar, glucose, and we react it with oxygen. Our bodies have got things in to help with this activation energy, enzymes to help break the bonds. So you don't need as much energy to start it off. And then we release a lot of energy, and that's why we're hot here, because we're releasing energy. And then you end up with your products. So we breathe out carbon dioxide and wee out water, and those have a lot less energy than the food that we ate. So if we did this backwards, this is what plants do, take in carbon dioxide and water and make glucose and oxygen. So they're basically doing this exact same reaction backwards. So you see that plants have to add a lot more energy to start with. They have carbon dioxide, the bonds between the carbon and the oxygen need a lot of energy, this activation energy, a lot of energy to break those bonds to start with. Once the bonds are broken, then the plants can fairly easily put carbon atoms together to make the sugar molecule. There's lots and lots of steps in plants for that to happen. So the one diagram could be read different ways. So forward reaction, respiration, backwards reaction, photosynthesis. So we can work out this is the activation energy for the forward reaction. And if we looked at it, this would be the activation energy for the back reaction. So you notice that the endothermic reaction, this one, this is an endothermic, this reaction, you're adding energy to the products have got more energy. The endothermic activation energy is a lot larger, and in fact it equals these two together. So the energy from here to here is equal to the activation energy of the reverse reaction. Okay, so a lot of our diagrams so far have been a bit vague on here, but you could add some units. So this is carbon monoxide and nitrogen dioxide, and this is carbon dioxide and nitrogen monoxide. What type of reaction is that diagram? Is it an endo or exothermic diagram? You can see it's gone from reactants down to products. Your products have got less energy than the reactants, so they've released it. So this is exothermic. You need to get this shape in your mind. It's opposite to endothermic. Okay, what is the magnitude? What's the number and sign, positive or negative, for the change in H for the forward reaction in kilojoules per mole? So you can see it counting down here. This is 150. So each of these are 50. This is kind of not really exactly, so it's not 175, it's a bit less. 175 would be about here. So it's about 165. And this is 400, and that is a bit more. That's maybe about 60. So if we look at the difference, your change in H is not right. What on earth is going on? Oh, here we go. The energy in your products, sorry, that's here, is minus 400, and we're looking at the difference between here and here, really. So you can almost do this in your head, can't you? Going 100, 200, 200, and that's 65, then there's 40, then there's 35 here, so it'd be 235. So you can see that that gap is 235. This is getting all fancy. Negative, take away a negative is positive, so you're adding on that, so it's negative. It's negative because it's exothermic. What's the activation energy for the reverse reaction? So the activation energy for the reverse reaction is from here to here. So it's from 100 to about 300, and that's about 40, so 60, about 360. Yep. Okay, so that's from here to here. Activation energies are always positive numbers. So that's positive 360. Alright, pause it and do this question. I shall start talking about it now. Okay, the activation energy for the forward reaction is 62. The activation energy for the reverse reaction in kilojoules is one of these. So I find it much easier if I do a quick little diagram. What type of diagram am I going to be drawing for the forward reaction? An exothermic one. Yep. So your activation energy for your forward reaction was 62. 62. And your change in H here, the difference between the reactants and the products, is 38. So you can see that if you draw your diagram, that the difference from here to here, activation energy for the reverse, 62 plus 38 is 90, 100. And so it's 100, the activation energy. Okay, these are exam style questions. Okay, I'm not sure which exam this was on. But instead of drawing the activation energy to connect the two lines, they've just done the energy in the reactants and the energy. You can tell that this is a reactant because it's going down here to the products. Down here to the products. So these are actually two different reactions. This one's turning this into this, and this one's turning this into this. Okay. What is the change in H for the following reaction? So this particular reaction, you find where this is. So here, the products of both of these is this reactant. So we're going from this reactant to this one. Okay, so we're going from here to here. So we want to know what this gap is. As well as going from here to here, this is not exactly the same. It's double. So we're doing this twice. So you can see that from here to here, the gap is 170. From here to here, from here to here, the gap is 312. So the gap from here to here is going to be 312 minus 170. 312 minus 170. I should have done this first. Presumably it's 142. Yep. We want it doubled. So we want 284. So the question is it positive or negative? So we're going from our reactants up to our products, adding energy, endothermic. So it's A. Okay.